Today, we're going to continue looking at sequences, series, and power series. In particular, we've been trying to determine if a given series, AN, say, converges or diverges. And we've got a lot of tests. These are usually called tests for convergence, but they don't do a good job of testing for convergence. It's not we run the test to find out what's going on. We kind of have to know what's going on before we run the test. And that's the point of all these tests anyway. The point is not learn the test, learn how to use the tests so that we can run them so that we can determine things. The point is to internalize the tests so we can, and know what the tests are telling us so we can quickly determine if a series converges or diverges. So let's remind ourselves, since it's a Monday, let's remind ourselves of the things that we know. So first, this is the big one. This is the necessary but not sufficient condition. If the limit of the terms is not 0, then the series AN diverges. So this is important. This establishes a necessary but not sufficient condition for convergence. So this is a necessary but not sufficient condition for convergence. If a series converges, then the limit of the terms must be 0. But we don't get it in the other direction. If the limit of the terms is 0, the series might converge. It's necessary but not sufficient. From this, we can get the contrapositive, which better states the necessity of the limit of the terms being 0. If the series AN converges, then the limit of the terms must equal 0. So this is just the contrapositive of the previous statement. And we always get the contrapositive. If A, then B, then if not A, then not B. A implies B implies the contrapositive, not A, not B, implies not A. So from this, we know that the limit of the terms has to equal 0, but it's not that the terms go to 0. It's not that the terms go to 0, it's how the terms go to 0. That's the important takeaway here. It's not that the terms go to 0. It's about how the terms go to 0. So another way I phrase this is to say that it's not that the terms go to 0, it's how the terms go to 0. Are they going to 0 fast enough? That's kind of a shorthand way of thinking about it. Are they going to 0 fast enough? So are the terms going to 0 fast enough is the way we can think about it. All right. So that was the first thing that we had. If the limit of the terms is not zero, then the series diverges. Then we had the integral test. This is where we take the terms of our series and make a continuous function out of them. So it's kind of a little crossover event. Like at the beginning of some television series, it's going to take place in the same universe as an existing series. They have a crossover event. So like the first episode of Law and Order, The Next Big Thing, will be one of the episodes of Law and Order, The Previous Big Thing. And then thus the universe continues. The Law and Order cinematic universe. So the integral test, we determine that a series converges by integrating the terms as a continuous function. So we have to have a series So here's a series that we're trying to determine converges or diverges, and we make a continuous function out of it. Not part of the given, that's just the first thing that we do. We think of the terms of the series as a continuous function. And the test says, if the improper integral converges or diverges, then the series converges or diverges. So if the improper integral converges, then the series converges. Similarly, if the improper integral diverges, then the series diverges. So good news, we can determine if a series converges by integrating the terms. Bad news, we got to integrate the terms. We want to avoid that. That sounds like work, and that's something that we should always try to avoid. So an important result of the integral test was the P series. P series is fine, it stands on its own, but I always frame it as a result of the integral test because it makes us think about the mechanics of the integral test and why we would want to do something like this in the first place. I don't know if I should have like separate ones. This is not a structure that I use all the time, So a P series is a very simple series. It has a form 1 over n raised to the p power. And this converges if p is strictly greater than 1 and diverges otherwise. I like to think of this as a result of the integral tests because if we integrate 1 over n to the p, if p is greater than 1, then the n is still in the denominator in the antiderivative. And then when n goes to infinity, that antiderivative will go to 0. But if p is less than 1, then when we integrate, the n will be in the numerator, and so the antiderivative goes to infinity as n goes to infinity. And then in the middle, if p is equal to 1, we get the natural log of n. And then as n goes to infinity, natural log of n goes to infinity. So it's a natural result of the integral test, and it gives us a nice boundary. In the case of rational functions and radical functions, this is how we determine if something is going to, if the terms are going to 0 fast enough. Are the terms going to 0 faster than 1 over n? And if that's the case, then we get a convergent series. Next on our list of things, we had the comparison tests. So in the comparison tests, we have, there's two versions. And we're looking at two series. We're going to start off with let AN and BN be series, because there's going to be a comparison. So we start off with two series. One of the series is the given series that we're trying to determine converges or diverges, and the other one is a known convergent or known divergent series. So one is the given series. One is the given series that we're trying to show converges or diverges. The other is a known convergent or known divergent series. So we're taking our given series and comparing it to something that we know. And there are two versions of this. One is a direct comparison and one is the limit comparison. So let's take a look at that. Oops. In the regular comparison test, we have one series is going to be the bigger series and the other series will be the smaller series. So in the regular comparison test, we start off with two series because there has to be some comparison. So we'll say let AN and BN be series. And then in addition to this, one of them has to be the bigger series. So we can squeeze one between 0. And the other series. So here we have a bigger series. And we have the lesser series. Actually, greater and lesser is more formal than I usually am. I'm usually like all bigger and smaller. Should just be honest with how informal I usually am when I'm talking about series. So if the smaller series diverges, then the bigger series diverges as well. If the series AN diverges, then the series BN diverges as well. That makes sense. If all the terms in Bn are greater than those of An, and when we add up all the terms in An, we get infinity, then when we add up all the bigger terms, we're just going to get infinity again. The other direction, if the bigger series converges, then the smaller series converges as well. If we add up all the bigger terms and we get a finite value, it's not like we're going to be able to squeeze in infinity underneath that. So if the bigger series converges, then the smaller series converges as well. Note that if the smaller series converges, then we don't know anything about the bigger series. And the other way around, if the bigger series diverges, then we don't know anything about the smaller series. If the smaller series converges, or if the bigger series diverges, then we get nothing. And I say to you, good day. We get nothing. So if the smaller series converges, that doesn't tell us anything. That's not helpful. Or if the bigger series diverges, also not helpful. Because we're either saying this sum is more than some finite value. That could mean it's a finite value, or that could mean it's an infinite value. Or we're saying this sum is an infinite value. And so the sum that's less than that is either also infinite or finite. Doesn't tell us anything. So since we're not always going to be able to make this comparison, we have the limit comparison. So let me do an example. So for example, the series 1 over n squared plus 1. When we look at the series 1 over n squared plus 1, we should suspect that this converges. If we look at the important terms, this is 1 over n squared. When n is a billion, who cares if we're adding 1 after we square the billion? The 1 doesn't matter. The 1 is the dollar that you spent on the lottery ticket. The n squared is the $10 billion squared that you won. But notice that the terms 1 over n squared plus 1 are strictly less than 1 over n squared. And 1 over n squared is a convergent p-series. So we got to prepare our court case because we're going to be on Judge Judy tomorrow. So we'll say, since the series 1 over n, the series in question, 1 over n squared plus 1, is strictly less than the series 1 over n squared, and since the series 1 over n squared converges, the series 1 over n squared plus 1 converges by the comparison test. Notice that we did not use the test to determine that the series converges. We use the test to show that the series converges. We already had to know that it converges. That's how we chose 1 over n squared. So that's an important thing to note. We chose 1 over n squared for the comparison. We chose 1 over n squared for the comparison because we knew it would work. We know that 1 over n squared plus 1 will be less than 1 over n squared because if we increase the denominator, the fraction gets smaller. The shares for Ocean's 11 are smaller than the shares for Ocean's 10. Typically where criminal organizations fall apart. If you're willing to kill someone, kill one of your coworkers, you know, it's like, hey, if we divide by 11, that's one thing, but if we divide by 10, then we all get more. But then you got to worry that your coworkers don't say, hey, you know, if we divide by 10, that's one thing, but if we divide by 9, that's another. And I don't know if we can trust this guy to say, it's like, oh, that convinced us to kill this other guy. So you see how it works? That's why they all had to be friends in Ocean's 11, because otherwise they just start killing each other for a bigger share because they understand fractions. True. If a clown in Gotham City says, hey, let's do a heist, don't join in. Just say, nah, I'm gonna sit this one out. Because you know that that guy understands fractions. So notice that we can't do a comparison on 1 over n squared minus 1. Because the inequality goes the wrong way. If the smaller one converges, that doesn't help. It doesn't help if the smaller one converges. Fortunately for our heroes, well, fortunately for our heroes, we can look at this one and say 1 over n squared converges. It's not exactly a p-series, but it looks like a p-series. So we knew this converged because 1 over n squared plus 1 will behave like a p-series. Our thinking, the series 1 over n squared plus 1 and the series 1 over n squared minus 1 both behave like 1 over n squared. That's why we make the 1 over n squared comparison. That's how we determine that these series converge. When we look at them, the plus 1 and the minus 1 don't matter. It's the 1 over n squared that is the key. And so in our mind, we're thinking that these series behave like 1 over n squared, so we know they converge. That's what's going on in our minds. These series behave like 1 over n squared. For large values of n, the plus 1 or the minus 1 doesn't matter. Only the n squared matters. So we're thinking for large n. You're either taking 1 and dividing it by a billion, or taking 1 and dividing it by a billion plus 1. And that's just not going to make enough difference to count. I guess it depends on how small your things are. You are going to care about those places if you're trying to, I don't know, like write the coordinates not just of your city or your house or a room in your house or a corner of a table in your house, but like a coffee grain on the corner of a table in the house in your city on planet Earth. You're going to need a lot of decimal places. Maybe the +1 and the -1 are going to matter. But for large values of n, for actual large values of n, we're not talking about the distance from San Francisco to Los Angeles, or from San Francisco to the moon, or from San Francisco to Jupiter. I'm talking about actual large numbers. I'm not talking about the difference from one end of the Milky Way to the other. I'm talking about actual large numbers. N is going to infinity here. And the size of the Milky Way is nothing compared to infinity. So for those kinds of numbers, +1, -1, doesn't matter. So we want to quantify this when we say something, one series behaves like another series. And we quantify behaves like with the limit comparison test. Because we're talking about doing a lot of hand wavy when we say 1 over n squared plus 1. It's pretty much like a 1 over n squared. You can't see me, but every time I do that, I wave my hands. I'm like, oh, it's pretty much, But we don't like to wave our hands at things. We're not engineers here. It's that's good enough. We actually have to make things rigorous. I'm just kidding, not making fun of engineers. It's the physicists I make fun of. I'm just kidding. I'm not making fun of physicists. They understand very, very complicated things. Mathematicians, that's a group of clowns right there. What are we talking about? Oh, the limit comparison test. Once again, we're making a comparison. Once again, one of the series we know, and the other series we're trying to show. And once again, we're not testing anything. We actually have to know whether the given series converges or diverges for this to work. So we start off, let AN and BN be series. We're going to look at the limit of the ratio of these series at infinity. If the limit, as n goes to infinity, of the ratio of one series to another series is equal to a non-zero constant, then either both converge or both diverge. This is one of the one of the ways where we can describe one series behaves like another series. So for example, if we have the series 1 over n squared minus 1, when we look at this thing, when we look at the important pieces, we see 1 over n squared. This is taking place in our mind. So 1 over n squared is a convergent p series. It's easily recognizable as a convergent p series. So that won't require a lot of justification. So we'll make a comparison with 1 over n squared. And we'll say since the limit as n goes to infinity of the series in question divided by the series that we know, since this limit is going to equal a non-zero constant, and since the series 1 over n squared converges, the series 1 over n squared minus 1 converges by the limit comparison test. At this point, Judge Judy looks over at our opponent and gives them a dirty look. Because how did things get this far if your opponent's argument is this solid? At which point they edit out your opponent saying the truth. It's like, well, you pay me to be on here, and so instead of paying the guy $2,000, you pay me $5,000. I give him $2,000. I still walk away with $3,000. And so for some people, being humiliated on television is worth that. So notice that it's important that before we make our conclusion, we have made two statements. The limit from the comparison test is equal to 1, which was a non-zero constant, and we're stating that the known series 1 over n squared converges. That way, since we got a non-zero constant, we can say both converge. But we have to say that the known series converges to make that happen. Just like in the comparison test. One of those series was a known convergent series or a known divergent series. So we have to state the known one converges or diverges. So for example, if we've got a series that looks like 4n squared minus 5n plus 6 over 7n cubed minus 8n squared plus 9n minus 10. If we look at what matters in the numerator and the denominator, the numerator is a 4n squared. The denominator is a 7n to the third. Minus 5n and plus 6, when n is very large, plus 6 is not going to matter. When n is 10 billion, The 50 billion is not even going to matter. That's nothing compared to 4 times a billion squared. So in the denominator, we can make the same argument that the only thing that matters is the n cubed for large values of n. For small values of n cubed doesn't matter. When n is close to 0, that negative 10 is starting to say, hey, I'm the big kid on the block here. But that's for small values of n. When n is very large, the only thing that matters is 7n to the third. So in our mind, we're thinking this is like the series 4n squared over 7n to the third, ignoring all the small stuff. Then we just simplify the n's. So we get 4/7, take out the constants, and we have a 1 over n, and that's divergent. So we already know that the given series diverges. But we're going to be on Judge Judy tomorrow, and we got to make sure that all of our stuff is in a row. So we're all set to go. We're going to make a comparison to this series 1 over n. This is our known. And we'll say since the limit as n goes to infinity of this series 4n squared minus 5n plus 6 over 7n to the third minus 8n squared plus 9n minus 10 divided by 1 over n, which is multiplied by n over 1, is equal to the limit as n goes to infinity of 4n cubed plus some stuff over 7n cubed plus some other junk is equal to 4/7, a non-zero constant, and since the series 1 over n diverges, by the limit comparison test, both converge or both diverge. So we can conclude that the given series the most important part is that our conclusion is that the given series diverges. Something we knew before we started writing this argument. Something that we knew when we looked at the n squared over n cubed and say 1 over n diverges. And so this given series diverges as well. So although this chapter is framed in as a bunch of tests that you're supposed to run, the point of the test is to not learn the test so that you could use the test to show that something converges. The point is to look at what the tests are telling us, because for some of these tests, like the comparison tests, we have to know if a series converges or diverges just to use the test. Do I make a comparison? Do I use this function? So given this series, do I use a convergent series or a divergent series in the limit comparison test? Because if you try to use the wrong one, the limit comparison test won't work. If you don't get a non-zero constant, then the series do not behave like each other. So if you do this part here and you don't get a non-zero constant, then you did the test wrong. And that means you get to make no conclusions. And no conclusion is not an answer. It's important to think about that. We don't get to write as an answer to a multiple choice question, no conclusion. That is essentially leaving it blank. That is being so afraid of getting things wrong that you're unwilling to guess. But if I say, does this series converge or diverge? I'm giving you a multiple choice question. You should answer, just guess. Maybe your instincts are better than you think they are. If you just leave it blank, all I can do is apologize for the damage that we've done to you by making you have all these tests and making you feel bad for getting things wrong. The worst thing that we do to our students, to our young people, to our children, for Christ's sakes, is make them bad for getting things wrong. In school, the whole point of going to school is to learn things. You're going to expect people to get things wrong now and again. You know what I mean? When you're afraid to answer a question, that's why. Because when you were a child, someone made you feel bad when you tried to guess and you guessed wrong. And that's a damnable offense for all those people that did that to you. In their defense, they were told that that's what they were supposed to do. So really, the offense lies with all of us for not looking at things, saying, this is wrong, and then doing something about it. You know what I mean? Anyway, tomorrow, we're going to talk about more tests, more ways that series can go to 0 fast enough to get convergence. That's going to do it for today. Everybody have a good day. I'll see you tomorrow, and thanks for playing.